So welcome everyone, and I know we do have a large group, so I'm sure we'll have more joining us and as we go along. But thank you for choosing to spend your Saturday with us. And we have more than 200 people from at least 15 countries that have registered to join us today. So we're really excited. I'm Alice Lara. I'm the CEO of the SADS Foundation, and I have been here for 22 years. I wanted to just start off with talking a little bit about you, our SADS community, and just a couple of quick facts, because I know we don't always let you guys know, but we really collect information and want to know about you and what you need and how we can help. So our community that we have in our registry is over 15,000 members. Some of them are families, and we don't know everyone in the family, but it is a large group of all kinds of SADS conditions, and it's growing every year. We send over 7,100 e-newsletters to family members every month. So hopefully they have some useful information. And we also have, and have always had since the beginning of my time at SADS, nearly 70% of our funding to do the work that we do comes from our community, you guys. That's large and small donations, volunteer fundraisers, and people that give an automatic monthly gift, to name a few ways that you support us. And I want to thank you, and we all, the staff wants to thank you for being supporting our work and making it possible for us to continue. Today, we're partnering with the Canadian SADS Foundation, and really good friends of ours since their founding, and they are partnering on this conference with us. And I'd like to introduce and thank Pam Husband, who is the founder of the Canadian SADS Foundation and their leader. Pam, take it away.
Thank you, Alice. Yes, you know, I forget how long we've been friends, Alice. And so I'd like to say, so thank you to the US SADS Foundation. Over the last year, and particularly the last 6 months, we've had wonderful collaborative activities ongoing. So thank you to all of Alice's staff as well, because they have provided us with guidance and training to help us with our own social media posts. And of course, we've collaborated extensively with the US in terms of the postings that we're putting out to our SADS community. And we're just really grateful for that, and really feel that they're not just our collaborative partners, but our friends. And so just wanted to say that. Honestly, too, it's just wonderful to be here, even though it's Saturday morning. And Alice makes all these plans and then drags me in, which is really important. So I just wanted to greet everyone, say hello. It's nice to see that there's Canadians out there. And just to reiterate a little bit about what Alice mentioned, we have really significantly increased our following over the last 6 months or so, particularly the last 3 months, I would say, largely due to Evan Kruger, who I know is here today, and also is kind of he is the driving force behind the social media campaigns that we put out there. We think they've been very successful. We do have a great following, but we don't know who you are. And by that, I mean a great Canadian following, but also a great international following. And as Alice pointed out, we'd love to hear more from you, how we can help, what kind of topics and pieces of information that are more helpful to you, and so on. So we hope you'll connect. I see there are a couple of old friends. So I'm dating myself. I see a couple of names of people in Canada that I've known for quite some time. I don't want to, you're obviously here to hear people way more important than I am. But just also to talk a little bit about funding. The Canadian SADS Foundation has really been a little bit, well, more than a little bit, somewhat dormant over the last couple of years, and we're trying to rise from the ashes, if you, to use a metaphor. And so we're planning some hopefully attractive fundraising campaigns. And one of them will be our online auction, which we have scheduled for September the 24th to October the 1st. And so please contact us if you're interested in donating, if you're interested in helping, and so on. And I think I should stop talking. I will go back to Alice though and say, Alice, is there, oh, I did want to mention very quickly though, our live streaming program that we started in December of 2023, hosted by Dr. Shu Sanatani, who this live streaming program has been very successful. We have a different guest every month. We're generally airing this live the third Tuesday of the month, noontime Eastern time, noontime Toronto time. So do your math depending on which side of the coast you live on. And you can also review these live streams on our YouTube channel after the fact. And there's information on our website to help you find your way there. And that's another reason why we'd like to hear from you, because we'd like to hear what kinds of topics are of interest to you, and perhaps what kind of guests or who, you know, suggestions for guests and so on. So I'll sign off now, and have a wonderful day, everyone.
Thanks, Pam. That was great. And I would encourage you to check out some of their programs. They've been really good, different than our SADS Live. And I think the upcoming one, I think, should be really interesting. A mystery guest that is a fascinating guy. So in any case, check those out. And if
yes,
you need
July the 18th. July the 18th is the next one.
Good. So I just want to come back to our team. As Pam said, we have 7 people at SADS that really work to serve you and put on all these programs and everything else we do. So we are still really tiny, but we've been working really hard to this year on a lot of new programs, some of which you'll hear about a little bit today, at least about the science part. But one of our big things this whole year and the end of last year is genetic testing, to really encourage everyone with the SADS condition to get tested, to get their family tested, and to know that that is the standard of care. And we've also been working really hard with the medical community to help them figure that out for those physicians, cardiologists who don't know anything about genetic testing or how to order that for a patient. We've got some tools as well that we've developed. So that is really important to us now as we go forward into even more of the genetic age with gene therapy, which is another piece that we've been working hard the end of last year and will be all this year to sort of educate ourselves and educate you and figure out what it's all about and what do we need to know, because there are trials that are in the pipeline. And so one of them is actually on clinicaltrials.gov as we speak. So it's coming, and it will, you know, we'll need to really know what to do if you want to volunteer or not, all that kind of thing. So stay tuned for more of that. And then please, as Pam said, let us know if there are other things, questions you have. We do have our SADS Live twice a month now. We always get lots of questions there. So we would love to, any feedback that you have would be great. And then lastly, in this piece, I want to thank all of our sponsors for today. And you saw that on the opening slide, because without them, we could not have put this program on. Armgo Pharma, Boston Scientific, Cardurian Pharmaceuticals, Medtronic, and Tenaya Therapeutics are our sponsors for today's conference. So thank you very much to them. And now we'll be hearing from our medical experts. We have medical experts from the US and Canada, all volunteering their time and expertise to educate us. So we really, really appreciate those partners. And we get all of our information from these international experts. So thank you, thank you. And now I'd like to introduce Genevieve Eccles, who is our Family Support Director. She's going to talk a little bit about what she does and what things that you can access.
Thank you, Alice. As a family support director, I have the pleasure to meet and talk with many of you and provide support along your journey with your SADS condition. This year alone, we've talked to nearly 200 families from all over the world, and almost half of those families are new to SADS. We've reached many more families through social media, webinars, support groups, and also through this conference today. Thank you for being a part of our family. Families reach out to us for support after they've been newly diagnosed or having a family member that's newly diagnosed. And sometimes they also reach out to us after they've been diagnosed for a while, but they're entering a new stage of life. And that brings up new questions and need for different support. Being diagnosed with a SADS condition can be scary, but we're here to help you navigate your diagnosis so you can live and thrive with it. There are many different ways we help families get the support they need. One of the services we receive the most requests for are physician referrals, and we know how important it is for each of our families to see an expert. So we connect families with these experts through our physician referral network so they can receive an accurate diagnosis, screening of family members, and the best treatment plans. When you're diagnosed with the SADS condition, you might feel alone, and many families who reach out to us have never met someone else with their condition. One of the things that we do is help facilitate that peer support through one-on-one connections and through monthly support groups. It's wonderful that you're all here today to make those connections with other families. Another way we support SADS families is by providing education and resources. Some of the things we provide are materials for each SADS condition, information on genetic testing, and kits containing information to keep kids safe at school. And these are just a few of the things that we're able to provide for families. Like Alice talked about, we also have our SADS Live program. We do webinars and conferences like this one. And one of the things that we love about SADS Live and our conferences is it gives you an opportunity to ask your questions to the experts. A couple of big projects that we've been working on this year are our first ever externally led patient-focused drug development meeting and scientific adjunct meeting. We held the ELPFDD on June 20th, and this meeting helped to inform the FDA, researchers, companies developing new therapies, and medical professionals about what it's like to live with ARVC. We had an amazing response with over 203 people attending live. This response would not have been possible without our wonderful SADS community. While this meeting focused on ARVC, it also benefits the SADS community at large by creating more awareness about what it's like to live with the SADS condition and its treatments. As a follow-up to that meeting, we're holding a scientific adjunct meeting on July 20th. And this gives the medical community, researchers, and those developing therapies the chance to take what they heard from the ELPFDD and discuss how they can apply it to improve the care and treatments of those with ARVC, and also to use the patient voice to help guide the decision-making process. Throughout the ELPFDD meeting, and nearly every time we talk with families, we hear about the emotional toll it takes living with a SADS condition and the treatments. We hear about anxiety and the lack of access to mental health resources and counselors. We've been working really hard to do something about this. We recently had an amazing genetic counseling intern named Rebecca Altagracia Rojas from Massachusetts General Hospital. And we worked with her to put together some resources, including places to find counselors, websites, and books to read that will help with PTSD or grief or the different mental health aspects of living with a SADS condition. We'll have these resources up soon on our website and hope they will help SADS families reduce the mental health burden of living with a SADS condition. We couldn't do any of these things without each of you being a part of our amazing SADS community. We hope this conference provides you with answers to questions and the knowledge you need to better understand your SADS condition. And now I'll turn the time back to Alex.
Sorry, I have to unmute. Oops. Thank you so much, Genevieve. And I really know that everyone who talks with you appreciates the help that you provide and the compassion that you have for our SADS community. Now, I'd like to take a moment to remember a very special friend and a volunteer to SADS, and I'm already starting to cry. Sorry, and it's amazing scientist, Dr. Andy Golden, who passed away on July 1st this year. Andy came to us in 2011 and he was looking for a home. And basically that's exactly the way he put it to me. He wanted a community to join, to be a part of, and to participate. And he was an amazing participant and volunteer. I think all of us have benefited from his caring compassion and from all the amazing things that he did to volunteer. We all have stories about Andy and memories about what he did and what he gave to us. And it was way more than what we provided him. At least I always felt that way, but I know that he was a special part of our community. I wanted to just tell you one quick story about to illustrate some of the things that he did in terms of, figuring out for himself what he wanted to do and what was needed. At our conference in 2017, which actually was in Toronto with the Canadian SADS Foundation, Andy sat in on the Timothy Syndrome group, which for the first time had some research presented by some of the scientists working on Timothy Syndrome. And then he went back to his lab at NIH, he was a researcher studying various rare diseases, and he made a Timothy worm to study. And that was sort of unbeknownst to all of us at first. He just decided he would do that, and he did that. And some amazing work that he learned just from knowing the community, from meeting the kids with Timothy Syndrome and studying Timothy Syndrome in his lab at NIH. So he then fast forward, became the very first board chair of the Timothy Syndrome Foundation when they broke away from us. Although I never say they did that, because they've always been and still are really close to us. And we really support them. So anyways, in honor of Dr. Andy Golden, we would like to announce that we are naming the SADS Foundation Volunteer of the Year Award, which he won quite a few years ago, after him. Thanks, Andy. We will never forget you. And I don't know if, Alex, if you or any of the family members want to say anything now or not. It's totally up to you.
His brother's on the line. I can see Hal. Hal, do you want to say anything? I can see your picture. Are you okay? You're on mute. No, you're all right. You're on mute, honey. You're on mute.
You hear me now?
Yes.
This is just amazing. And I know what it meant to him. And I'm not going to be able to say much more because it's hard for me to talk right now. But I know what it meant to him, this organization. And he's just so humble. I didn't even know half the stuff he did, because he just did it and didn't really talk about it. And, he was just too humble. And when you read the memory wall, everyone says the same thing. And he was just an amazing person, but a really amazing brother. So I'm going to go back to Alex, and you can, and Zoe, you guys can finish up. But thank you guys, and that is just amazing.
So yeah, did you want to say anything? Are you good? So Zoe doesn't. So on behalf of Zoe and me, I really want to thank you for providing Andy this home. Our longtime life together, I have memories of the search that he undertook in order to find a landscape where he could provide the support, the care, and the comfort to families. His first try was really to try to connect here at Hopkins with, just to give you a little history and to know how special you are, was to connect with the pediatric congenital heart disease practitioners and support community at Hopkins. And I can say this with experience, Hopkins being, because I was on faculty there for 20 years, Hopkins being Hopkins was like, we got this, we don't need you. And he felt, he was disappointed by that. And he tried so hard through multiple times to get something kicked off there, because he knew how important it was to bring people the message that despite the physical challenges that they were facing as individuals and as families, that an incredibly normal life was possible. And because that's the way he lived his life. As much as he went through from a physical perspective, if anyone ever had the excuse to be self-indulgent or complaining or depressed or down, it was him, because it was one thing after another, and he never was. So he really wanted people to know that outside of what it was that they were facing, there was a life as full as you could make it. And that was for children, for adults, and for families as a unit. When he found SADS and he found Alice and he found this community, he found, Hugh said it, he found a home. And from there, I really watched him blossom and really throw himself into the support that he so desperately wanted to give people. It was just such a mission for him. And Andy, being a science geek and a worm guy, wanting to figure out some of the science behind it and how he could contribute from that perspective. So he was always looking for those two angles, the support and the science. You can't imagine how important it was to him that he found this home. And then ultimately, eventually met Catherine, developed a deep friendship with her. Christine, who's also on the line, Christine Bedame, and found his way into the Timothy Syndrome Foundation. So from my heart and Zoe's to yours, thank you for giving him that space, for recognizing that he could be a tremendous resource for you, for not turning him away or minimizing him in any way, and really giving him that landscape for him. It was enormously gratifying, and it's very moving to hear that you've created this, the volunteer award moving forward in his name, and you're naming it that way. So for Zoe and me, we're here to continue his legacy of support, both emotionally and scientifically, to SADS and the Timothy Syndrome Foundation. Until we depart this earth, you have continued support from us, and I'm sure Hal feels the same way, and Hal and his family. So from our hearts to yours, an enormous thank you. We've, I think, really only begin to grapple with how big a loss. So.
Yeah. Well, thank you. And I really thank Johns Hopkins for totally not recognizing and appreciating.
I know, missing the boat won't
They
have been the
lost
first time.
somebody really special. Yeah. So thanks. And we just have a really short clip that Anna put together with some of memories of Andy. So we're going to play that next. But thank you so much for joining us this morning.
Thank you all. Andy will be missed. I'm Marcia Baker, and I am the SADS Program Director. It's my honor to introduce our first presenter, Dr. Andrew Landstrom. Dr. Landstrom is an associate professor of pediatrics at Duke University School of Medicine. He's a physician scientist and cross-trained in pediatric cardiology, electrophysiology, human genetics, and molecular physiology, and he leads an active research program there at Duke. Dr. Landstrom's talk today is personalized medicine in the treatment of SADS conditions, from drugs to denervation to devices. And for questions for Dr. Landstrom at the end of his presentation, you can post them in the chat feature, and we'll welcome Dr. Andrew Landstrom right now. He's on the line.
Good morning, everybody. I'm going to attempt to share my screen. Can you all see it okay? Wonderful. And a quick apology in advance. I am joining you from the lovely Carolina Beach, North Carolina, which is just wonderful to be able to vacation a bit and have your family jump in the ocean. It is terrible in terms of internet access. And so if anything slows down, please, please, please just let me know and we will improvise. But I am absolutely thrilled to be here. Thank you for spending your Saturday with us. A big thank you to the SADS Foundation and the Canadian SADS Foundation for the opportunity to be here today. As kind of your leadoff hitter, I'm not sure if you all have seen the agenda, but Alice and Marcia and the rest of the SADS team have put together just an incredible lineup of talks from experts from around the world for you today. And this talk is designed to sort of be an introduction. We'll touch on things that future speakers may touch on a bit more in depth. And I already saw a question or two about gene therapy in there, which we'll touch upon, and then we can get to in the Q&A. But also know you have got a phenomenal, phenomenal speaker coming up in Mario Delmar to ask about that pharma trial. But again, it's my pleasure to talk to you a bit about precision medicine in the treatment of SADS conditions, from drugs to denervations to devices. I have no disclosures or conflicts of interest, although I do receive salary support and research support from the following not-for-profit or federal organizations. So we're going to cover 4 main topics today. We're going to talk about SADS conditions as genetic diseases, which really forms the basis of the rest of our conversation, which is on how genetic testing can be individualized to personalize your care, and how we can use that individualized information to treat SADS conditions in a very specific way, depending on the person. And I'll share with you my dream for the future, which may be a bit ambitious, but I think it's good to dream big. So when we talk about SADS disorders, we're talking about a number of different diseases that all fit under sudden arrhythmia death syndromes. They can range from anything from long QT syndrome to short QT syndrome, just meaning that the time it takes for the heart to reset can either be too long or too short. And just like Goldilocks and the 3 Bears, it needs to be just right. And so when it's too long or too short, that can be a pro-arrhythmic condition. Brugada syndrome, which we'll touch upon in a little bit, is also a SADS condition, as is catecholaminergic polymorphic ventricular tachycardia, CPVT, and a related but quite distinct SADS condition that's relatively new is calcium release deficiency syndrome, CRDS. Arrhythmic cardiomyopathy, or the changing of the muscle of the heart to kind of a fatty scar, is another form of heritable arrhythmia syndrome. And then suddenly, if somebody has a cardiac arrest, a heart attack from an arrhythmia, and we don't know why, we often call it idiopathic ventricular fibrillation, or idiopathic VF. All of these have a genetic basis, and that really forms the foundation of diagnosis and precision care. So it's best to kind of get just a little bit of vocabulary as we're going on with our talk. And it's important to kind of realize that when we say genetic in nature, this is what we mean. So if we think back to biology 101, we have genes in our genome that I think of as like recipes in a cookbook. And each recipe makes a certain thing. Each gene makes a certain kind of protein in our body. We have ion channels in the heart that move electrons and electricity molecules back and forth to allow our heart to beat, because our heart uses electricity to do so. And we need a full complement of ion channels to make that electricity happen normally. And if our genes are good and those ion channels are good, our hearts are electrically quite stable. Now, what if you have a spelling error in one of the genes? We all have genetic differences that make us individual, but what if one misspelling happens in one of these genes that encodes, that serves as the recipe for an ion channel? Well, then that ion channel may be made with that spelling error built into the protein. It might be a little bit more dysfunctional than normal, and that may lead to electrical instability of the heart and arrhythmias. Or there can be what's called a loss of function mutation, where the spelling error is so big in the recipe that there's nothing that's made. The recipe loses a page and you can't actually make the end product, in this case, make the ion channel. And sometimes we call those loss of function mutations because there is no protein there. And so really, these are two major ways that you can have a gene spelling error that causes an arrhythmia syndrome. And this is really important when it gets to things like gene therapy, because you can imagine the therapy for one may not work for the other. One, you've got a mutation in a protein that's being made that's causing electrical instability, and the other, the protein's absent. And so you want to be able to account for these when we talk about precision-based therapy. And so if you have something like long QT syndrome, because it's a genetic disease, we can look for it in the DNA of the cells. And so shown here are actually the cells that live inside our cheek. So if you ever do what's called a buccal swab, or a swab of inside of the mouth to collect DNA, you're collecting cells that look like this. To me, they look like pancakes, a big blueberry on top. And that blueberry is the DNA inside the genome. And we can extract all that DNA and find the one spelling error. You can see, look, right here, where you go from single peaks to a double peak. And that's a spelling error that makes a spelling change in the protein. This is actually a picture of what it looks like to be an ion channel, if you look at it very, very close up. And then that single misspelling is enough to completely, in this case, make that ion channel non-functional. And so shown here, this is an experiment we can do in the lab called patch clamp. And all you need to know is that these big peaks that come up off the baseline here show normal electricity through that ion channel. But with a single misspelling, it can reduce that to essentially nothing. And so if you have long QT syndrome, this is how one spelling error in a gene can lead to a protein that's made, but completely non-functional, causing electrical instability of the heart. And because we know this, we can look for those spelling errors in those genes to be able to identify who's at risk, and then potentially treat those individuals in a very specific and customizable way. It's important to realize that many of these genes overlap. So for example, long QT syndrome can be caused by mutations in SCN5A, which makes the sodium channel of the heart, called NAV1.5. But if you have Brugada syndrome, you can also have mutations in the same gene. Those mutations just do different things. One causes long QT syndrome, one causes Brugada. Same thing for CACNO1C. We heard about this. We heard about Timothy syndrome in the thoughts that were given about Andy. Timothy syndrome can be caused by mutations in this gene, and it can cause long QT syndrome, Timothy syndrome, or short QT, depending on the kind of mutation. Conversely, if you have catecholaminergic polymorphic ventricular tachycardia, CPVT, that's most often caused by mutations in RYR2, which makes the ryanodine receptor in the heart. But you can also have mutations in that same channel that cause calcium release deficiency syndrome. And also things like the potassium channel can cause both short QT and long QT. So there's overlap. And this can be very complex, but it actually, in some situations, if you find that expert, can actually help to custom tailor therapies based on the genetic findings that lead to the disease. So gene testing is really important. Alice shared this earlier on about the importance of genetic testing, and I know SADS has been a big advocate in this space, and you should be too as patients and families, but gene testing is really central because genetic testing helps us to make a better diagnosis, helps us to identify family members who might be at risk, even if all the clinical testing looks good, because they still have that risk variant. And then these mutations are also really important for us to be able to provide precision medicine, medicine that is individualized to you and to your gene mutation, and also helps us to consider what might be prognostic challenges. That is, what might actually cause maybe a sudden death event. All these things can be genetic specific and individualized based on a gene test. So because of this, gene testing is absolutely central to this evaluation. This is what a positive gene test looks like. So this is an individual with long QT syndrome, and the gene test was positive for a mutation in the gene KCNH2. This is long QT syndrome type 2. And that mutation leads to a pretty big change in the protein, shown here by a star. And that means that the protein is actually not made very well. And then the gene testing company has come out and said this is a likely pathogenic variant. So if you have long QT syndrome, this is no doubt about it, this is the cause. And if you can get a gene test like this, it's actually helpful in many ways because it allows you to identify those at-risk family members as well as customized therapy, proving that the individual doesn't just have long QT syndrome, has long QT syndrome type 2. And the type of long QT syndrome matters. So if you have long QT syndrome type 1, which are due to mutations in KCNQ1, then we know that those individuals are a little more at risk of having an arrhythmic event that can be life-threatening during swimming specifically. What about the gene test we just saw for KCNH2, long QT syndrome type 2? Those individuals have a slightly higher risk of developing life-threatening arrhythmias with what we call loud auditory triggers, loud sounds, things like fire alarms that go off in the middle of the night and startle you. These individuals have to be careful about those loud sounds and realize that that can be a risk factor. Long QT syndrome type 3, which is due to mutations in that sodium channel we mentioned. Those individuals can have a little bit higher risk of having sudden death during sleep. And so it's important to realize that this is a major, this is one example of the major importance of that gene test because it allows sort of custom tailored precautions as to what individuals may face in terms of risk factors based purely on their genetics. And knowing the individual genetics and the individual SADS condition that each patient has is really important to being able to determine what the best therapies are. So for example, beta blockers, which we use frequently in many SADS conditions, are the cornerstone of treatment for catecholaminergic polymorphic ventricular tachycardia. But knowing that we have CPVT, we can also treat with a medication called flecainide if we need. Long QT syndromes, in particular 1 and 2, respond very, very well to beta blockers. Long QT syndrome type 3 responds well to beta blockers, and sometimes you can add additional medications like mixilotine because we know that the sodium channel is affected, whereas mixilotine may not be as effective in long QT syndrome 1 and 2. And then something like Brugada syndrome, I find really challenging to treat because their beta blockers are not really effective in this disease state. And so this is a perfect example of knowing one's genetics and one's SADS diagnosis as being really important to custom tailoring what medications may or may not be effective. Also, some SADS conditions may, in some situations, benefit from certain surgical procedures. This is a picture from one of Mike Ackerman's publications on what's called a sympathetic denervation surgery. This is typically for individuals who maybe they have arrhythmias despite being on really good medications, are having life-threatening arrhythmic events, don't tolerate the medications that they need. This can actually be quite helpful in certain situations. And essentially, the premise behind this is that just like beta blockers kind of cool off the heart and relieve some of the stress response of the heart, these nerves do the same thing. And so if they're removed, it actually acts like a beta blocker that's kind of permanent for that individual. Sympathetic denervation surgery. This is a what's called an inside the thorax image of where that sympathetic chain lies. So this is actually inside of a patient. This is inside the rib cage here. And you can see down here a lung that's been dropped and deflated so that the sympathetic chain can be identified. And that sympathetic chain is here, running along this sort of glistening streak here below the inside of the ribs. And this is what they'll go in, they'll identify, and they'll remove. And sympathetic denervation surgery. But importantly, this isn't for everybody, which is why that individualized approach to your care is really, really important. In some individuals, this works really well. In other individuals, it may not. So this is work showing how good sympathetic denervation is in the right patient. So this graph to the left shows numbers of patients on the y-axis, and on the x-axis, the number of arrhythmias those individuals have had. And on the left side of the hash line are individuals before they had the surgery, and on the right side are the same individuals after this denervation surgery. And as you can see, when properly selected, these patients are not, just these are higher risk patients. They have a lot of arrhythmic events. 9 of them in this cohort had more than 10 arrhythmic events. And then after the denervation surgery, nearly all had improvement in the number of arrhythmic events that they had. Moreover, this denervation surgery does have some side effects. For example, dryness of the skin, facial flushing. It's different from one side of the face to the other. And then rarely can have some more permanent things like eye droop. Those are rare. But this is one example of kind of a survey that went out to patients who would have this denervation surgery and asked them, hey, look, what are your side effects? And you can see here some of them very common, like dry skin on that left side, or color split between the sides of the face. But then they asked them a really interesting question. They said, knowing the side effects that you have, would you have gotten the surgery again? And overwhelmingly, 90% of the patients said, yes, for us, it worked really well. It helped us to be safer. And again, this is a really important finding for individuals who may be higher risk, and individualized therapy can help to lower that risk. And we have incredible new tools from the scientific research side to be able to leverage these exciting new discoveries to make new discoveries for SADS patients. One of them is shown here. These are called induced pluripotent stem cells, and they can be taken from any patient, any individual, from a baby all the way up to a 100-year-old. And with a little bit of blood, we can isolate a particular kind of blood cell, trick that blood cell into becoming that person's stem cells, and then convert those stem cells in a dish to beating cardiac myocytes. And so effectively, we can take a very sick child in our ICU and then model their heart in a dish with just a simple blood draw. And this allows us to learn a lot more about the disease process with a goal of being able to fix that disease in these heart cells before we move them to, say, small animal trials or potentially trials in people. The other major advancement is gene therapy. And I'll just touch upon this very briefly because you've got the expert coming up in Mario Delmar. But gene therapy, very broadly speaking, is defined as anything that modifies a cell's genetics or introduces a gene to produce a therapeutic effect. This is work by Mike Ackerman, published a couple of years ago, and there's lots of exciting follow-up work that's come from this. But Mike Ackerman took a step back and said, well, look, we have beta blockers that work well for long QT syndrome, but can we come up with a new therapy, a gene therapy, that in these high-risk patients might be a very valuable therapy to lower their arrhythmia risk? But if you remember, long QT syndrome has mutations in genes, and those genes tend to be expressed. So you've got kind of a challenge here, because in a normal long QT heart cell, you've got one copy of a normal gene, typically, and one copy of a gene that is got that spelling error in it, and that abnormal protein is being made. So you have to do something to actually remove the abnormal protein and then replace it with a good protein. And this is called silencing, where you shut down one protein from being made and then replacement of that wild type protein to supplement the loss. And so the Ackerman team dubbed this suprep, or suppress and replace. Suppress the bad mutation, replace it with an extra copy of the good. And you can see here just a little bit of data from that initial paper. So shown here on the our cells, these are cell tracings. And on the x-axis, this is time. And these are cells beating. And just like when these cells beat and your heart cells beat, electricity moves. And the amount of time it takes for that electricity to reset is the same in these cells as they are in the heart when they're all put together. And so as you can see here, if a cell takes longer to reset, like a long QT patient might, you're going to see that red line here is extended out further. The time takes longer. And so you can see that red line is actually a heart cell from a long QT patient. And there's different kinds of long QT patients here with different kinds of prolongation of that action potential. And that red line goes back down to normal when this suprep is given, this gene therapy is given, and that's shown here by the blue line. The black line is normal. So you see a black line that's normal, a red line that's disease, and then that blue line that looks just like normal, which gave us a lot of excitement that the suprep is actually fixing that underlying delay in repolarization. And then he's quantified here, showing that in these heart cells, that suprep can reduce that action potential duration, making that QT normal. And they're really, they're moving forward on this on many different diseases, as well as in rabbits, which is really, really cool, long QT rabbits. What about Brugada syndrome? Well, Brugada syndrome is challenging because there's no good medications for it, right? Beta blockers don't work very well for Brugada syndrome. So really, we don't have great medications for it. And so the question is, can gene therapy play a role here? Well, Brugada syndrome is due to loss of function mutations in that sodium channel. And so half the sodium channels are not made. The trouble is, the sodium channel is really, really big, way too big to fit inside a virus. And usually we use viruses to deliver the gene therapy message. And so this is work what we did in collaboration with Nod Bursak. Nod was actually the brains behind the operation here. He said, you know what, let's not think about putting the full-blown sodium channel into the AAV. Let's think small. Let's think of a sodium channel. It might be actually small enough to fit inside one of these viruses. And he came up with BACNAV, which is a bacterial sodium channel. So up here is a picture of the human sodium channel, and it's massive. And it's got these big 4 domains that it needs to be able to make sodium current. Well, BACNAV is essentially one of these subunits, one of these domains in isolation, and that fits into AAV. And he's done some incredible work, and we've just sort of helped him out to show that this actually works in heart cells. You can actually use a virus, put this bacterial channel in, and it actually replaces the sodium channel of the heart. Lots more work to do to show that Brugada syndrome could actually respond to this, but very exciting that there's this small molecule that actually replaces the wild type SCN5A function. And then finally, I think I saw a comment in one of the chats about what about arrhythmic cardiomyopathy and PKP2? Well, if you take a step back, arrhythmic cardiomyopathy, I think of as a disease of the cardiac desmosome. You might be asking, what the heck's a desmosome? I think of a desmosome as being like the rivets on your jeans. So the rivets on your jeans are there to make sure your pocket doesn't come out from the side of your jeans. Desmosome does the same thing. A desmosome holds the ends of the cardiac myocytes together. And so just as if that rivet comes out, or there's a defect in that rivet, the pocket may come loose. Same thing, if there's a defect in the desmosome, those cardiac myocytes can pull apart. So this is a cardiac desmosome. This is a scanning electron micrograph of cardiac cells. See the beautiful striations here? And these desmosomes are those rivets that hold the ends of the cardiac myocytes together. And we know that 80% of pediatric onset DCM is gene positive, and the most common gene, PKP2. And so I'll share just a little bit of data that has made gene therapy for arrhythmic cardiomyopathy a real possibility. And I won't steal Mario's thunder about trials and those kinds of things, but it's data like this that I find very compelling. So this was presented by Tenaya Therapeutics at one of our gene therapy meetings a couple of years ago, or 1 year ago. Essentially, if you give a mouse arrhythmic cardiomyopathy by taking out PKP2, that's the most common gene lost in arrhythmic cardiomyopathy, those mice die very quickly, they get arrhythmias, and their heart dilates and fails. If you deliver a virus that replaces PKP2 to normal levels, it goes back to normal. And not just preventing disease, but really incredibly, if you wait for that heart to start to fail, get very fibrotic, fully arrhythmic, you can still actually reverse that remodeling in this mouse model with delivery of PKP2, which is, I think, a really stunning finding. And so this has really driven forward the idea that maybe we could be using AAV for PKP2 replacement for arrhythmic cardiomyopathy in people. Just so that you have a resource you can follow, there is a amalgamation of all the gene therapy trials. You heard a little bit about clinicaltrials.gov. This is also a resource for gene therapy trials worldwide. So something you can use to keep an eye on the literature, which is really exciting and advancing very, very quickly. What about devices? Well, a device that you may have heard of or may even have is an ICD. And these can be epicardial, these can be transvenous, they can be subcutaneous, where they're under the skin as opposed to in the major blood vessels, or no ICD at all. And the decision of who to give an ICD to is actually a very individualized question and depends very specifically on the disease state and the risk of the patient. And in our closing couple of slides, one of the things that we use to really individualize approach here is an implantable loop recorder. So oftentimes we need to know, gosh, was that fainting episode heart-related or was it not heart-related? Because if it's heart-related, I'm worried that it might be an arrhythmia. And so one thing that sometimes we do for patients when we really need to know, are those fainting episodes arrhythmic or not, is an implantable loop recorder. These things are tiny. They're little tiny thumb drives that can go under the skin, and that can go with you wherever you go and actually detect the arrhythmias in the heart and wirelessly transmit to our center. And for example, a child we follow at CPVT who was having fainting episodes that we were kind of worried about, we were actually able to capture them on these links and show that this heart rhythm is actually normal. She actually was fainting because she wasn't eating enough breakfast in the morning. And so we didn't have to do anything crazy because this was non-cardiac. We just made sure she ate, gave her a note so she could have snacks in the morning at school. Whether or not the therapies are given to each patient, there is a universal need for prevention, right? And so I strongly encourage everybody to know how to use an AED. SADS, as was mentioned very briefly at the start of this, has very specific plans that serve as wonderful templates for how you can actually engage with your school to come up with a plan for prevention if something were to happen. And then Project Adam is another foundation that's out there to directly outreach to schools to help them drill for having an emergency action plan. These are things that while our therapies may be individualized regardless of the patient, we talk about these things universally with all of our patients. And so finally, can we predict SADS disorders? Well, as the cost of the human genome has fallen precipitously, it's become easier and easier to sequence individuals at birth. And this is work that's been done in sick babies primarily, just to show you the power of what we call predictive gene testing. And that is figuring out early on the diagnosis that may have lifelong implications. And so these are studies that have been done for sick babies that are in the ICU, the NICU, the neonatal intensive care unit. And what they found is these babies, oftentimes they're quite challenging to figure out what's wrong, right? We don't know what's wrong. We're bringing in experts, trying to figure out what the diagnosis is of a child. Well, things like exome and genome sequencing in these babies has revolutionized our ability to diagnose them. And we can come up with a diagnosis in 50% of these infants when every other expert in the hospital didn't know what they have, which is really amazing. And in doing so, we save the hospital system the money, we save people money because we're not delaying a long diagnosis many, many years, upwards of $2 million per individual. And it can happen very, very quickly. Specifically, this study done by Stephen Kingsmore, they were able to arrive at a genetic diagnosis in less than 24 hours. And so this is the promise of predictive medicine and predictive genomics. But like anything, there is always a downside to this. Can we predict disease before it happens for SADS conditions? But what's the flip side of that coin? Well, oftentimes we don't know what we find, and we may be finding something that's completely incidental, and we don't know what that means for individuals going forward. And so we have to be able to balance that with our ability to detect early risk. And that's where incidental findings come in, such that if you're looking, what if you found a variant you didn't know you were looking for? How do we know if that variant will actually cause genetic disease down the road? And this is one of my favorite cartoons. It's got a physician talking to Kermit. Have a seat, Kermit. Well, I'm about to tell you, it comes as a big shock. He was not expecting to get this information. He's a puppet, but in fact, he is. There are a number of genes that are considered actionable. So if you're doing genome and exome sequencing, that these genes are considered something you have to tell the patient and family if they agree to get that information. And a lot of these are SADS conditions. And we know that if we do this, we're going to find disease in lots of individuals or disease-associated variants in lots of individuals. And so being able to interpret this is really, really important if we're going to predict disease in the future. And we have some tools that are starting to do this. But for now, the challenge is how do you spot the signal through the noise? How do you spot the one variant that's going to actually cause disease? And this has driven a lot of individuals and companies to explore precision-based genetics for predicting disease in these infants very, very early on in life, which I think is very exciting, but again, challenging. And just one quick cautionary tale. This is actually not a SADS condition at all, but this is a cancer condition where women in a family can be predisposed to having breast or ovarian cancer due to a single mutation in a gene called BRCA, the BRCA1/2 cancer gene. Well, this is a cautionary tale because this family was told that their BRCA gene mutation was very, very severe. And many women in the family actually went on to have bilateral, both sides, prophylactic, preventive mastectomy, removal of their breast tissue, only to find out down the road that this variant actually wasn't that risky at all. And so one cautionary tale, there's tremendous potential to being able to predict risk, but in families like this, we have to remember we have to do it wisely. But I think if I had to share my dream, I think we are beginning to be able to have the conversation to be able to detect SADS conditions, even at birth, even in children that we don't think show any evidence of disease before they get sick. And with the new revolutionary discoveries of gene therapy on the horizon, I actually think that in our lifetime, we're going to be able to predict at-risk individuals before it occurs, and then maybe even treat their disease before they get sick. So maybe that's a bit of an ambitious dream, but I think it's a dream that we can start talking about. And so your take-home points from our time together. Genetic testing is important for all SADS conditions. The details of the genetic test is important and can confirm an individual's diagnosis, guide treatment, identify risk factors. Gene therapy is a promising treatment down the road that requires individualized approach, and decisions about ICD placement and loop recorders should be individualized. All of this means definitely seek a SADS expert before you proceed with any of these things. And so with that, I'll acknowledge my wonderful team, especially the ones who worked on the BACNAV project, and acknowledge our funders, and I welcome any questions. Thank you all very much.
Thank you so much, Andrew. And we do have a few questions that have been posted in the chat. So first one from Ryan Parks. What do you think about the upcoming Rocket Pharmaceutical trial, RP-A601, for ARVC PKP2 conducted by Dr. Barry Greenberg from San Diego, ?
Yeah, Ryan, superb question. So we touched upon this very, very briefly, and I actually won't give too much information because in about an hour, you've got the expert who's Mario Delmar, who's actually, if I'm not mistaken, intimately involved with that trial, giving you a firsthand account of it, except just to say that because PKP2 is the most common gene mutated in arrhythmic cardiomyopathy, that the idea of potentially replacing that gene has really led to a lot of excitement. So I'll see if Dr. Delmar can expand upon that, but it's very, very exciting. Very, very exciting indeed.
Okay, and thank you, Andrew. Darren asks, what is your recommendation for testing family members for those of us who are gene elusive, but have ARVC as defined by MRI, echo, EKG, etc. testing?
This is a common question that we get in clinic. So gene elusive simply just means that you think you probably have a genetic condition, in this case, arrhythmic cardiomyopathy. You get the gene test, and that gene test says either we don't know, it's negative, or maybe there's a variant of uncertain significance that the SADS expert who's reviewing the test says, I don't think this is it. So we know you've got the disease, but the genetics remain unknown. So in that circumstance, because there's that uncertainty in that variant, then you do not want to use that variant for testing other members in the family. You don't want to do that unless you're certain that that variant is it. Because if you don't have the variant, you might say, oh, you don't need to be followed for your arrhythmic cardiomyopathy risk. But if that variant wasn't actually it to begin with, then that risk is still there. So generally, for risk, for gene elusive families, we say, we don't know the cause. We tend to follow variants just like we follow patients. We do genetic follow-up, and sometimes that VUS clarifies itself over time. But in the meantime, or if the gene test is negative, we say, well, we have to presume that the other family members are at risk because we can't prove otherwise. And so we follow them clinically with periodic clinical evaluations, especially for arrhythmic cardiomyopathy.
All right, thank you. And I just want to let you and the group know that Dr. Mario Delmar had to record his presentation. He's not going to be able to be with us live, so we'll have a recording from his presentation. And he did say that we can share his email with those of you that have specific questions about his talk on gene therapy later in the hour. So more questions here for you, Dr. Landstrom.
Please.
Hunter indicates for denervation, what's the definition of poorly controlled long QT? And let's see the second part of that. Is it available for those with breakthrough events despite faithful use of beta blockers?
Great question. Maybe I'll take the latter first. I'm not sure why some patients don't respond to beta blockers. Some patients simply don't tolerate them. They feel really crummy. They feel tired, and that tiredness persists. Sometimes it can make depression a bit worse. I wish I knew why that was. Some patients simply just don't tolerate it. Or there are patients sometimes that the disease is so severe that despite being on a fairly high dose beta blocker or even additional medications, that there's breakthrough arrhythmic events. Gosh, I wish I knew why that was too. There's a lot of really interesting studies that perhaps the type of mutation, the other gene mutations in the genome that we don't often talk about might influence a particular major gene mutation, but right now it's really unclear why some patients have that variable response to therapy. But the ones who I think are probably the most likely to benefit from a denervation surgery are individuals with typically catecholaminergic polymorphic ventricular tachycardia, which is very hard to control in some patients with just medications, and some very sort of higher risk patients with long QT syndrome. For me, I define high risk as, for example, in CPVT, as having breakthrough arrhythmias, particularly ones where they're symptomatic, which is why we fuss about symptoms like fainting. Symptomatic breakthrough arrhythmias despite maximum therapy. And that may be maximum therapy because we don't go any higher for our medication doses. They're already getting the maximum dose, or they can't go any higher because they can't tolerate those medications. And so in those types of situations, denervation surgery, I think benefits those individuals quite nicely. For long QT syndrome, a lot of those same principles apply. Risk can also be directly measured there by the degree of QT prolongation. So whether that QT is markedly prolonged might be a risk factor that, in concert with other things like symptoms, symptomatic arrhythmias, breakthrough arrhythmias, can lead someone to say, well, gosh, maybe that denervation surgery would benefit you. So I think it's really important to have that conversation. Just like these therapies are all individualized, that conversation is very individualized to you, to your risk, to your family, your genetics, and your SADS expert can help you with that.
Thank you. That's great. Hunter has another question. What are the negative issues, if any, with gene therapy?
My goodness, there are a lot of things we should be aware of. And so, you may remember back in the 90s, there was a big push for gene therapy, and then there were deaths. A young guy named Jesse Gelsinger who died, kind of halted gene therapy. It's important to realize that even now, with the advances that we have made, that is a possibility. There are individuals who have died from gene therapy. The benefit right now seems to be outweighing those horrible, tragic deaths, which is why it hasn't stalled like it did back in the 90s. It's moved forward. And so if you're talking about gene therapy, it's important to say, like, these are experimental therapies. We worry about what those side effects may be. We're trying to go in to fix one thing of the heart, but oftentimes the other organs could get involved. The immune system is a big problem in these patients, and the immune system can cause death, even if the gene therapy worked. And so that is something that really has to be weighed. That's why these clinical trials need to take time. The science needs to be there so that when you get offered something like a phase 1 trial, like Rocket Pharmaceuticals, like you just want to know what that risk profile is. And for me and my patients, I tell them just to be informed, utilize good information. I think SADS is a wonderful organization who's built gene therapy into a lot of their education. So go to trusted sources like the SADS Foundation to get more information and know what those side effects are, because they're nothing to just sort of just shirk, in my opinion.
Very good, thank you. Okay, let's see. Ruth asks, are there considerations to integrate SADS conditions into newborn screening?
Good question. Right now, no firm plans that I'm aware of. I think the science is really, the promise is there, but that peril is still there. So I'll give you an example. So if we genome sequence healthy babies who are born every day, trying to find the risky variants for SADS, right? The gene mutations for SADS, we actually will identify a lot of variants in the genome, mutations that are kind of suspicious. And we'll identify them at a much higher rate than there are SADS conditions in the population, which means that if we were to do that in a wide, broadly these days, today, we would label a lot of people of being at risk for SADS conditions who are not actually at risk for SADS conditions. And so right now, I don't think it's quite ready for us to be doing this, but the tools are rapidly improving. And I would hope that in the coming years that we can get smarter about that sort of risk prediction, because I think it's going to be more and more of a possibility going forward.
Thank you. All right, Carl notes, you noted patient preference data, i.e. 90% patients experience side effects, but would do denervation procedure again. Current advocacy efforts include promoting the Benefit Act at the Congress, and to have patient experience data used by FDA and drug and procedure approval processes. What is your experience, if any, having such data actually being factored into this process by FDA?
That's a great question. I'm actually not that familiar with that process. I know that before FDA can give clearance for a new therapy, that data involving efficacy and safety is central to their consideration process. And so without that data, it really cannot move forward in an experimental or an investigational way. But specific to, I would probably need to engage in a bit more of conversation with you about kind of what your questions are more granularly, except to say that the FDA does not do this in a box and really requires that sort of preclinical data to be done well. And to show a clear benefit over potential safety issues to be able to move forward, even in an investigational sense.
All right. Thank you very much, Andrew. I think that addresses most of our questions. We have some that we'll save too for our Ask the Experts with Mike, Shu, and Hari at the end of our day. So let's see. There's one more here. Ryan asks, what do you think about the upcoming Rocket Pharmaceutical trial? I think we asked that, I think, already, didn't we?
Yeah.
And I'll give you, Ryan, I'll pass along Dr. Delmar's email address. He said he would address some questions, so I'll provide that to you directly. All right. Thank you, Andrew, very much. We appreciate your time and taking time away from your beach vacation there.
No problem. My pleasure. Thank you all.
All right. Take care. All right, and next we have Brynn Dechert, who is a pediatric nurse practitioner in the electrophysiology department at Mott Children's Hospital Congenital Heart Center in Ann Arbor, Michigan. In her current role there at the University of Michigan, she cares for patients with sudden death conditions, children and adolescents with arrhythmias, and those with pacemakers and ICDs. And she's been caring for pediatric arrhythmia patients for almost 20 years. In addition to her clinical role, she has multiple research interests in pediatric patients with arrhythmias and sudden death conditions. Brynn is a board member of the SADS Foundation and is an active contributing member of our medical education committee as well. So her talk today is how to get the best care for you and your family. So welcome, Brynn.
Thank you. Thank you so much for having me. Marsha, can you see the slides?
You're good. Yes.
Great. Thank you. Thank you. I'm so excited to be here today. It's a rainy day here in Ann Arbor, Michigan. Hopefully it's nice wherever you are, but I'm going to be talking about getting the best care for you and your family. Like Marcia said, I'm a pediatric nurse practitioner, but I do obviously focus on the entire family when we're taking care of our kids. So we're going to cover a couple things today. We're going to talk about how to find the right care, what to expect from your team, how to ask questions to your providers, and sources of information outside of your provider team. So we first want to start with that not all cardiologists are the same. It is very important that patients with SADS conditions do see a SADS expert. And the group at SADS really has captured the experts across the country, actually internationally as well. And if you have any concern or any question about where to be seen with the SADS condition, please talk to our group at SADS. They have a physician referral network specifically that can help you find the expert that's in your area. The next thing is, again, how to tell if your doctor is an expert. You want to ask, if you're going to do your own research, the best questions to think about is how many SADS patients do they see? You want to make sure that you're not the only one. You're not the only patient with long QT that they've ever seen, the only patient with CPVT. You really want to make sure that they care for many patients like you. Also ask, do they have a specific arrhythmia clinic? In many instances, SADS experts may be an electrophysiologist. That's a heart rhythm specialist. They also can have a SADS expertise without being an electrophysiologist, but we want to make sure that they have a special arrhythmia clinic for those patients. And then also a SADS advisor. This is what I was mentioning from the SADS Foundation is, are they interactive with SADS? Are they on the list? And that is how we really keep our patients seeing specialized people. And like I said, the SADS Foundation can help you find an expert pretty much anywhere. And so that is a definite resource to find the right cardiologist to take care of you and your family. So evaluation and follow-up. So we're going to talk about, what you might need in follow-up. And the first question is, what tests do I need and why? So depending on what condition you have, the tests would be tailored to you. We don't just across the board do tests just to do them. So in some instances, we may do, in most cases, actually, we do an EKG. Sometimes we do follow-up exercise tests, and exercise tests lets us know what your EKG looks like and if you're going to have any arrhythmia with exercise. So it's a very controlled situation. It often uses either a bike or a treadmill. And you don't have to be perfectly fit in order to perform an exercise test. We just need someone that is able to be coordinated on either a treadmill or a bike and in order to do this. And what we do is follow the EKG the entire time that you're exercising. It does give us a lot of information. So you may be asked to do an exercise test either, kind of periodically, once a year. That's up to your provider. Other tests could be a Holter monitor. That can be either 24 to 48 hours for a short term, up to 2 weeks for a patch monitor, or even longer in some instances, depending on what your provider has. And that basically records every single heartbeat for the time that you're wearing it. And then the data is sent back to your provider. Sometimes patients need an echocardiogram, and that's an ultrasound of their heart. In some instances, patients need an MRI, and that's a test that involves laying in the MRI scanner. I know that some people may be concerned about claustrophobia with that, but we really have come a long way for those tests. I think Dr. Landstrom was talking about implantable loop recorders, which we may need to look at the data from those. Some patients do have ICDs or pacemakers that need to be looked at while we're in a clinic visit. So there's a large gamut of things that we could test for or do in any one clinic visit. The next question, how often do I need follow-up? That also is dependent on your provider, how you're doing, and the condition that you have. In most of our patients that are kind of smooth sailing, we see them, one time a year. Patients with a lot of arrhythmias or concerns, we might see more often in follow-up. So it really depends on how often, it depends on your condition to decide how often you need follow-up. And the other thing you want to find out is, who do you contact if you have concerns in between your next visit? In my institution, it's me. Usually it's either me or my partner, and we are both nurse practitioners trained in this area. If I don't know the answer, I can ask the physician as well. We're usually the nurses or the NPs may be easier to contact. Many times the physicians can be doing procedures and things like that and may not be able to answer your questions. So most of the time, you'd probably have an allied professional like a nurse or an advanced practice provider like myself in order to answer those questions. And I will tell you that at any time I don't know the answer, I can find it for the patient. In some instances, if it's a lot of discussion that we need to have, we've been setting up virtual visits for our patients in between, so they don't have to come back to our clinic. If we need to have a long discussion, more face-to-face discussion, we've had a lot of luck with our virtual visits, and we do that quite often. And I know that Dr. Ackerman and other physicians across the country also do virtual care in order to save a trip back to the hospital. Genetic testing and counseling, that's very important too. I think there's been a lot of talk today about why you should be tested. Marsha, I think I'll probably skip over this since I know we've probably gone over that. It is important to be tested if there's any concern, and I think family members as well. So who needs to be tested in the family? We usually do first-degree relatives to start with. So if a child has been, turns out to have long QT syndrome or something like that, the parents are usually tested. And what steps do you need to take? Many times that the SADS provider, and I would say this is another question you want to ask your SADS provider, is do you have a genetic counselor? And that's an important piece of the pie, because genetic testing alone does not give you all the information. You really do need an expert who can review it and also review it with you and talk about what it means. So in our institution, we have a genetic counselor that contacts all of our families with genetic testing questions. They help coordinate the testing and follow up on the results. So that's another question I would add to my list is, do you have a genetic counselor? So the steps that you have to take is actually letting the genetic counselor take it on. They will actually do all the work. Sometimes they can mail you the kit, which can be a swab in the mouth. Sometimes it's a blood draw. Just depends on what test it is. But the genetic counselor really can do everything for you. So topics to discuss with your provider. Our treatment options. There's more than one way to skin a cat, that old saying. So I think you want to make sure that the treatment, just like Dr. Landstrom was talking about, is tailored and personalized to you and your needs. We do a lot of what we call shared medical decision making. And so we're out of the kind of old school way where we just providers told you what to do. We really do sit down with our families and their patients and make sure that their treatment that we're discussing works for them. You may want to talk about medications and the side effects. This is important to know what side effects are worrisome, what side effects, can we kind of tolerate, how long do we expect these side effects. Sometimes when we start a beta blocker, that's a common medication that we would use in many of these SADS conditions. Side effects can be, usually the first 2 weeks and then may get better. And so that's what we usually say to our families is see what happens after 2 weeks. If it's still really bothering you, let's talk about a different treatment. You want to ask your provider about exercise and sports. I think that is also dependent on your provider and also the condition you have. Again, this is a dynamic discussion with our families. This is something that we share together on how to decide the risk level for exercise and sports. And what the provider does is talk to you about your options and what the risk might be with exercise. And then together we decide what might be the best for you and your family. You want to discuss definitely your family history with your provider. So if before you have a visit, it is important that you see if you can do some digging. If you can't get all of the information, the genetic counselor is actually very good at getting this information and eliciting this history from you. And they ask many questions about your family members and if they're alive and what, if they have any illnesses and things like that is important. You want to talk about the symptoms you should be aware of. So again, this is dependent on your condition, but you want to know what things are what we call red flags, what needs an immediate call to our office or even sometimes emergency care, or other symptoms that may be able to wait and have a discussion. And then again, what do you do if you experience symptoms? And I think your providers do a really good job or should do a really good job to tell you, this is a red flag, you call 911. This is something we need to hear about that day. This is something that we can talk about, as time goes on. So what we do as providers is tell families when to get a hold of us immediately. All right, so moving on to what to do for your appointment. I think the SADS has a great website that tells you a lot of information. And this on their website, it talks about preparing for your appointment. So you want to choose your top 3 to 4 questions. As we know, providers do not have an infinite amount of time. We do try our best to spend as much time as we can with each family member, but unfortunately that can't be hours and hours and hours. We just don't have that time in the day. So choose your top 3 to 4 questions, but also know that if you have more questions beyond that, there usually is someone you can talk to via portal message, email, contacting them via phone. So if you have other questions in between your visits, do not hesitate to call your providers, especially the advanced practice providers or nurses that can answer these questions and answer them, very well in between the visits. Taking someone with you is important because it's hard to remember all the stuff we may tell you. And I will say, I will tell a family something and I think I'm being very perfectly clear with what I'm saying, but it's how everyone perceives the information that we're provided. So if you have two people there, then you probably can get the information between the two of you on what was discussed. And again, you're always welcome to call with clarifying questions. The SADS website has a list of questions that you may want to write down and have ready. I think it's important to organize your thoughts when going into a clinic visit. That is, I actually love when I see a family, when I walk in the room and they have a notebook of questions because they're very organized. That makes my job so much easier. So having all of this organized in your mind is important so you don't miss anything. How do you find accurate information? We know that there's a lot of inaccurate information out there. Websites are great, but they're not always accurate. So the first place to start with is your healthcare team. Your healthcare team can really answer the questions for you and are willing to do so. And I think you don't have to wait to the clinic visit to do that. Now with, like I was talking about, virtual care and portal messages and things like that, we can answer questions all the time. Our portal messages are not open on the weekends, but I often will get them when I get in Monday morning and I'll message families back and forth. SADS Foundation is an excellent place to find accurate information. And I will tell you that the gang at SADS, if they don't know the answer, they're going to find the answer for you. So they're going to contact someone who will know the answer and they'll do that legwork for you. And they have a large database of people they can get information from. And I think that's really helpful and a great place to start when talking with your provider. You are the most important person on your healthcare team. So we know that as providers, we want to make sure that we are talking to you, even our teenage kids or even 8 and 9-year-old kids, we want to make sure that they're understanding the information. So we give the information the best we can in language that can be understood by everyone. We know that you know yourself better than we do. And that's why we want to have discussions and why most of our decision making or all of our decision making is shared. We're discussing this together because, again, you are the most important person on your healthcare team. The more you know, the better prepared you are. So really taking on your diagnosis and learning about it. We tell our parents the same thing. So, as a mother of a 15-year-old, I am trying to get my son to be more responsible and take on his own care. He does not have a SADS condition. He actually doesn't have many health problems at all, but I want him to be understanding what he wants to do in his life. So same thing with your children is making sure that they understand the condition at an early age, even if it's basic, understand the medications they're on, understand what medications they should avoid. I mean, it's just like a kid with allergies. They have to know what they have to avoid. So really educating your children and making sure they're part of the discussion is great too. So SADS website, like I said, we've mentioned several times today, it is fairly new and looks amazing. It has a lot of information on there. It's a really great place to find the information that you may need. And again, if the information doesn't make sense to you, then you contact your provider. As a group, I would say as a SADS referral group, we do manage our patients, not exactly the same, but very similar. We all are up on the guidelines and part of the guidelines and doing this research. And so if the SADS website doesn't have the answer you're looking for, your SADS provider can answer that as well. There's another website that's out there that's shared with SADS too called upbeat.org that can be helpful for information on SADS conditions as well. That information was created by SADS providers and pediatric specialists. So that's another place you can get that information. What can you get on the SADS website? Condition-specific information. So you can, find out information on long QT syndrome or CPVT, ARVC. All those can be found on it. We use our physician referral network all the time. This is a group of physicians that are experts in SADS, and we've vetted them over time by watching their research and seeing how they care for patients. So we have a great referral network. There are support groups that are excellent. These are, if I remember correctly, on Tuesday evenings, and these support groups are virtual and have done such a wonderful job bringing people together to have these discussions. The SADS webinars on Fridays are amazing. That started during COVID, and it has really done such wonders for our families, keeping them connected, giving them information. I know this is kind of spreading out into our SADS Canada as well. So people internationally now are able to be part of these webinars that really are excellent, where you can ask a lot of information and learn together. It's a great way to bring people together. There are research opportunities you'll see with your providers, and also the SADS Foundation website can give you information on what research opportunities are out there. There's registries for certain diseases, Brugada and CPVT. There's a lot of information about long QT syndrome. One of the research opportunities that we had recently was something called the LIVE trial. And that was a great way to get families involved. And really, you didn't have to do anything extra. It was just us getting the information and putting a lot of patients together and learning a lot from it. Genetic testing information is highly available on the SADS website to know where to get genetic testing. And SADS works very closely with genetic counselors. Many of the members of SADS are genetic counselors, so they have a big connection with them too. These are some of the pictures that we think about when we have SADS conditions, and that's the blood draws and the patients that may have issues with passing out and things like that. And even though these pictures are graphic, sometimes it is kind of what we think about when we're seeing our provider. So hopefully this doesn't gross you out too much. And I'd love to answer any questions that you may have. I'm here and able to answer any questions. And like I said, if I don't know the answer, I can usually find it somewhere and get back to you. So thank you for letting me speak today. It was great.
Thank you so much, Brynn. And we would welcome any questions in the chat for Brynn. She has a vast experience working with patients.
It looks like Carol had a question about, I think this is for me, right? The noted importance of, there's a couple of things. I'll go back a little bit here and see what we found. All right, so the Abridge app is really helpful for appointments. It provides a transcript and summary of the appointment and highlights new diagnoses and medications. Rachel, thank you so much for that. We're always looking for better apps and better ways to get our patients information. So that is not something I'm familiar with, but I would love to look into that, especially since you speak so highly of that. And then Carl, you noted the importance of genetic counselors as part of a collaborative team. However, there is such a shortage of an access to GCs nationwide, particularly in rural America. Any advice for those who have a SADS expert but do not receive access to a GC? I think that there is a genetic counseling website, and I can't remember the name of it. Marcia, if you remember, or Alice.
The NSGC.
NSGC, that you can actually find genetic counselors, and sometimes they will do virtual care, in that way. So NSGC is a great way to find genetic counselors, and they're often willing to help. And I know that some genetic counselors out there can do kind of pro bono work in other areas. So that's where I would start with for that question.
We also have some information on our website.
There you go. And then,
yeah,
sorry,
because there are some companies that provide that will help with all aspects of genetic testing, including helping billing insurance and doing a whole report just for the patient and for the doctor. So, and they're really affordable, even if a lot of the insurance will pay for that, but they also are pretty affordable as an individual just to pay for that help.
And I just got a message from a genetic counselor who is on the call. She did confirm NSGC, and she did confirm that there are telemedicine for genetic counselors. So you can find a genetic counselor who may not even be in your area, but who can provide information via telemedicine. So we have done such a great job with telemedicine. It's one of my favorite things to do because it has really allowed us to see patients across the country. I mean, in Michigan, our patients could be 8 hours away. To save them a drive is great. So we may do a lot of our testing locally, meaning like where they live in the UP, and then we can look at that information and still provide the counseling over the phone. So Lori, thank you for your message. So nsgc.org is confirmed to find a GC that can do telemed for you. The Farrow family, very accurate from perspective of a mom and a wife who has been in many of these appointments. Thank you very much. We really appreciate your support here. And I know as a mom, and like I said, I don't have a kid with SADS condition, but I know how nerve-wracking it can be to raise children. And then Lori sent another message to me, findageneticcounselor.org. It's another way to find a GC. Christine, have you seen a child having both Brugada pattern and sinus node dysfunction and then recommended a pacemaker? At what point would an ICD be indicated? Christine, I think this is, a very interesting question, and obviously must be something, that your family is dealing with now. In children, we don't take lightly implanting an ICD. We know that there can be a lot of issues and psychological issues with an ICD. So I think this is something that you really need to talk to your provider about. There are two reasons why we might put in an ICD. One is called primary prevention, and those are for patients that we think are at higher risk for having an episode of arrhythmic syncope or sudden cardiac death. And then there are ICDs we put in after patients have arrests and things like that. So this is something I would follow up with your provider on. And then the sinus node dysfunction question, that's usually something that, again, is a discussion based on the symptoms that your child might be having before we just would jump ahead and put a pacemaker in. So I think it's something I would definitely continue to discuss with your provider. Marcia, I think I got them all, unless you saw any.
You sure did. Great job,
other-
Brynn, in following the chat. So they come fast and furious. So we appreciate your spending part of your Saturday with us, and have a good rest of the day.
Thank you. Thank you all. Take care.
And next we have a talk on ICDs versus S-ICDs and some of the differences and uses. Dr. Taylor Howard is our presenter. He is an assistant professor of pediatrics at Baylor College of Medicine and a pediatric electrophysiology with the Arrhythmia and Pacing Department at Texas Children's Hospital in Houston. Dr. Howard provides a full spectrum of heart rhythm care, including interventional procedures to manage arrhythmias. He is specifically interested in the management of patients with pacemakers and ICDs, and those with tachycardia requiring ablation therapy. So welcome, Dr. Howard.
Thanks so much. I am working on sharing my screen.
Very good.
I think that, hold on real quick. Looks like I'm running into a firewall issue. Let's see if I can allow this to go forward. All right, give me 2 seconds. I'm going to stop.
No problem.
Try to get this done.
As a backup, Dr. Howard, we could also have you email it to me and we can share them from our end.
That may be what I have to do, because it's not letting me. It's handed me a firewall and not letting me. Let me try one more thing, and then I will email them. And I'm sorry about that. I didn't realize that I had
no problem.
some sort of firewall
Sometimes
on there.
hospitals do have strict restrictions.
Yeah. Okay. Well, let me email them real quick.
Okay, I'm going to have you send it to Aaron at
Okay.
sads.org, ERIN at sads.org.
Okay, I sent it off and I'm gonna keep working until you guys get it, and seeing if I can. I'm young enough to where I should be able to figure this stuff out.
You did good in Houston when we were there for the children's
Yeah.
program. You did it.
Yeah, I know, it's always something, isn't it?
Yep.
So,
I'll check with Aaron here.
I'm checking my email right now. I'll let you guys know. Haven't gotten it quite yet.
yeah, it's a big file.
Oh, yeah, it might take a minute. Okay. Still waiting.
How many megabytes was it?
Yeah.
14.
14? Oh, we
Oh,
should.
there we go.
That's not too bad. You got it?
Mhm, mhm.
All right, great.
Okay, actually, can you see my
Oh,
screen now?
yeah, you beat me to it. There you
I'm
go.
winning.
Go
I
into
changed, I think I
PowerPoint.
just wrote some code. I feel like a hacker. All right, well, let me do this. Well, thanks for bearing with me, guys.
There you go.
Am I
That's the
okay
fun
to
part
get
being live.
started?
Go ahead. You're doing good.
Yeah.
Yes.
Well, my name's Taylor Howard. I'm one of the doctors at Texas Children's Hospital, and I take care of kiddos with heart rhythm problems. And one of my interests is taking care of kiddos or helping families along the journey as we make decisions about device therapy. And I know that is something that comes up for individuals with conditions that would put you in this room here today. So we're going to talk a little bit about SICDs and ICDs and when and if, but we're going to give a little bit of a wholesale overview. And this talk's a little shorter because I wanted to leave a little bit of room to tailor it to maybe where you guys might have questions about these types of devices moving forward. I wanted to say I don't have any financial disclosures for us. My objectives today are to discuss ICD basics with some discussions about SICDs and other types of ICDs, provide a background for who gets these, and review a little bit about what life looks like with the different types of devices. So just to normalize the playing field here, an ICD is an acronym, and it stands for Implantable Cardioverter Defibrillator. And they're made up of components, and they all have the same components, no matter what, if you're getting a subcutaneous or SICD or a transvenous ICD. What the main component is a generator, and the generator has a battery in it that's usually lithium ion type of technology, so it lasts for a really long time. It also has a capacitor, which stores charge in case a shock is needed. And it's got a computer system, a series of software that has it. Every ICD is a pacemaker. Not every pacemaker is an ICD. So to make an ICD, it has to have a capacitor that can store charge. And then up here is the header. And the header is basically like the plug, where the lead itself, which is a wire that usually attaches itself into the heart when we're talking about transvenous ICDs or within the blood vein ICDs, or it runs through the subcutaneous tissue above the chest wall. The job of the lead is to hear the heartbeats and to transmit the information back through the header into the computer system within the generator. And then if needed, you can kind of see this little coil here, this little metal part that you see this change in color around there. That coil begins to be a charged particle at certain times. So that's where you can pass the charge through from the can here, the generator, to the coil of the lead. And that's your that's the pathway of the shock if it is required. So ICDs come in different shapes and sizes. And so these are 3 that I had in my office from different major manufacturers. I have no bias or preferences here in case you guys were wondering here. And so the one in the middle is a company called Medtronic. And this is a Medtronic single chamber ICD. The newest version of it's called the Cobalt, but it's about the same size as the Avera, just updated technology. It's about 5 centimeters across and about 8 centimeters down or so. Then there's the Abbott Gallant VR here. That's the new Abbott. It's a little bit of a smaller profile here. It's about the same size functionally. They say the Abbott's about 10% smaller. When you're working with them, they're functionally the same size. And then you'll see the big guy over on the end. And this is an S-ICD. And the S-ICD requires a larger footprint because it has to have a bigger capacitor because the charges have to be higher in the way we deliver energy through an S-ICD. So it's about 8 centimeters across here, but it also goes in a different place. And I'll talk a little bit more about that, but it's a bigger device, as you can kind of see. There's also Biotronic makes ICDs. They're a European company. Or a German company, one of the two. I just didn't have one. I think they're fine. I'm not here to spread any messages about anything. So right here, these are the ways that we can implant ICDs. And so when we talk about a regular transvenous ICD, we make an incision under the clavicle, which is the collarbone right here, down to the pec muscle usually. And then over the pec muscle, we make a pocket and we drop this ICD in. Then we poke the blood vein there, the blood vessel or the vein that's draining the arm back to the heart. And we run the wire down into the heart across the tricuspid valve and then plug it into the right ventricle. And it is the normal kind of way that we do it or used to, I guess. That's the classic ICD route. And many people will have this or have discussions about it. In some patients that are too small to have an ICD, because at least at our institution, we start out offering ICDs when you're above about 55 pounds or 25 kilograms. And bigger is usually better on this, just as far as growth is concerned around the device. If you're too small, or if you have problems with your heart that would lead to difficulty with us getting an ICD inside the heart, you can have an epicardial ICD system. And an epicardial means outside of the heart. And this is not placed by me or people like me. This is placed by cardiac surgeons. And so there are various ways to this, but in some cases, you actually have to have a sternotomy, meaning a breastbone kind of opening like you would have open heart surgery. And in some cases, they can do what's called a subxiphoid incision, the xiphoid process that's right around here, and they can open up and then expose from underneath, but not all the time. In this case, the lead is actually, you can't tell, but it's placed actually directly behind the heart. They get all the way behind the heart and they run it alongside it. And then they put wires on the heart to sense the heart rhythms as well and pace the heart if needed. And then the generator box is placed in the abdomen below the heart there as well. And those are needed, like I said, if you're small or if you have anatomy that would prevent us from moving forward with the transvenous ICD. The next is a subcutaneous ICD as well. And so you can see that the lead right here is placed right along the sternum, which you can't really see the sternum because of the spine, but the sternum right here, and then it's tunneled all the way and then the back to the back. And the device is placed by something called the latissimus dorsi muscle, which is kind of on the back of your side, if you will. It's under your armpit and but towards your back. And the lead itself is placed under the subcutaneous tissue, but outside of the thoracic cavity or outside of your rib cage as well. As far as cosmetics are concerned, it depends on your size, but you can definitely see a bulge in these cases right here on your left chest usually. Here, you're going to have a scar on the middle part of your chest, and you'll potentially have another scar on the bottom and a bulge down near your abdomen. And on the subcutaneous ICD, there's a tiny little nick that we make right here to get this ICD lead in, and another tiny little nick here to tunnel it this way. And then the device does cause a bulge, but in some cases, people prefer it, in some cases not, but it's kind of on the back of your side. So most clothing covers it up under normal circumstances. But if you're a smaller individual, then you will see a definite bulge because it's a pretty large device on that as well. And so know those things going in. So who gets ICDs? And that's a big question. And a lot of that has a lot of different particularities to your diagnosis and your physician team and the particulars of your diagnosis. There's in 2021, there was a big PACES expert consensus guide on how we make decisions surrounding it. And you can see a lot of SADS people on here, Molly Shaw and Jeff Kim, Prince was on there, and Brian Cannon's on here. There are a lot of your friends from different places that you may go to are represented, a lot of different institutions, but this document helps make decisions on who gets ICDs and then when we implant them as well. And that could be an hour talk in and of itself, so I'll kind of skip over it. As it was being alluded to prior to this, there are two big buckets of that we talk about when we talk about ICD implantation. Primary prevention, which just means that an ICD is implanted prior to a person having a bad arrhythmia due to a perceived higher risk of one happening in the future. And then there's secondary prevention, where an ICD is implanted after a bad arrhythmia has occurred in order to deal with it more quickly if it happens again. In those cases, there are different conditions that have different degrees of evidence supporting primary prevention implantation. Like hypertrophic cardiomyopathy, for instance, has a fairly good evidence base behind it. But there are other conditions out there that where it's a little bit more of a nebulous or gray zone on who we primarily implant. In secondary prevention cases, once a cardiac arrest has happened, those are generally a little bit more worked out, and there's a little bit more of a clear path as well. So when you get an ICD, it's done in the operating room or the cath lab, depending on if you have a transvenous, subcu, or epicardial system. And almost certainly, if you're a child, you are under general anesthesia. If you're an adult person going through this, a lot of people do general anesthesia nowadays for it, but occasionally you'll have some twilight anesthesia or things like that. But it is not, I've done them both ways and people are comfortable under most circumstances. My preference for kiddos and teenagers is that I do general anesthesia for it, because I just have not had any complaints about that. And we have really good anesthesia that's really safe where I work. When we talk about risks of procedure, this is the thing that kind of on why we have to be thoughtful about ICDs, is that every procedure that we do has risk involved with it. And I look at risk in two different buckets. I look at acute procedural risk, and really we can kind of extend some of that risk out about a couple of months. And then I look at long-term risk for what does it mean to have an implantable cardioverter defibrillator walking around with you in that, and kind of that thing. So when we talk about acute risk, the best study that we have as far as kind of at time of implantation, the risk factor about 2.5%. If you extend about 2 months, there's not good pediatric data, to be honest with you, but there was a really big Dutch paper that came out with adults, and it was all implanted devices, ICDs and pacemakers too. And there was about a 4.5% risk of issues that needed reintervention. In total, there was about a 12% risk of any issue altogether, but a lot of those were able to be managed pretty easily. So I look at that, you have to actually go in for something. But the main things we worry about are bleeding, not life-threatening bleeding, but just kind of general bleeding that would perhaps cause some difficulties or may lead to infection. Infection in and of itself, reaction to the medicines that may be related to anesthesia, damage to the lung, like puncturing the lung as you try to do the thing, damage to the heart, like puncturing the heart. Abnormal heart rhythms can be seen during the, that's why we're here. The kiddos tend to have proclivities towards that. And then you can have mechanical problems like lead dislodgement and things like that might need to be done where you need to redo stuff. There's also long-term risks, and those mostly are related to mechanical issues, infection. You can have long-term valve damage if you have a transvenous device. Sub-Q devices are outside of the heart, and so they do not have that risk, which is a nice thing. You can have inappropriate therapies, which I'll talk a little bit more about, and you can have need for repeat procedures, which I'll talk a little bit more about. As we talk about need for repeat procedures, that's every young person with an ICD. So if you get an ICD when you're 10, I'm hoping you live till 80, and we're going to have an ICD potentially for 70 more years unless we figure something out. And so we actually are planning our next operation every time we do one. And that's why we have to be really thoughtful about how we get the first one in and how we manage those kiddos moving forward, because they're all going to need repeat procedures. The batteries nowadays are incredible. They're lasting 12 and 15 years on occasion, more on the 12 side, but it's not forever in a young person. Now, inappropriate therapies, these are when you get a shock and you didn't need one. And the latest studies on this are showing that this is becoming increasingly rare, but it's not zero. So the device technology and the companies that make devices are very focused on having this never happen. But the truth is that components break down, or people interact with things that may make it more likely that you have a device malfunction and it fires. The issue with this is that it hurts and people don't like it. I have yet to have a kid who's had an appropriate therapy that didn't appreciate it, but I've rarely had kids that have inappropriate therapies and they don't like it very much. And so as a provider, I'm very focused on not letting this happen. And the latest kind of studies that I've seen is around 9 to 10% over a long period of risk factor. So 5 to 10 years is what we're looking for, is exposure to that risk there. So it's definitely not zero. And it's more likely to happen if you have lead issues. And so it's just a plug to continue, if you have one of these ICDs, to keep sending your remote transmissions in so we can work ahead of that. So let's talk a little bit about living life with an ICD. So the lifestyle changes that go along with it, there are some, but honestly, it's very rare that I limit a kid beyond what their condition already has limited them to. There are a few issues. One, collision sports, I'm generally a no on. These are like rugby and football. I'm extreme sports, I'm a little wary of. This is particularly like motocross, like racing things, just because you can break the device. And then roller coasters, amusement parks, and circus rides. This is something I get a lot. I have actually never heard of a kid having an inappropriate therapy or anything bad happening to their device on a roller coaster. And I've also looked at a few blogs. I cannot find anything. That being said, there are some conditions that we deal with in the SADS organization for which people probably shouldn't ride roller coasters if it makes them real nervous. And I also worry a lot about how the containment system, if you're on a really rough ride, if you've got one of those shoulder strap things, how it rubs against the device and things like that, that could be too rough. So all that to say, be thoughtful about that. So household items and ICDs, I think that I'll show you a couple of websites here. So as we, the companies have websites themselves and they help you kind of manage these things there, but there are procedures that you can talk to your doctor about. But is you can look at their household items, and they have lists of things that are safe to use with your ICD. And all that to say, they're most everything there. It's pretty rare here that you find something that really meaningfully interacts with it. That being said, something like cell phones, they need, and ear pods and stuff like that, need to stay about 6 inches away from the device, mostly because they have magnets and they can change your device into a magnet mode and things like that. But otherwise, it's pretty rare we find something. The issues that come up are particular type of welding machines. And I'll show you these kind of things like car motors or alternators, electric fences, transformer boxes, things like that. Beach combers, like the metal detectors, and ab stimulators, things like that. So, but you can look on these websites. It has to be a pretty aggressively electric in order to mess with your device. Most things that I use every day, almost everything, I have none of these in my house except for a car. And as long as you stay away from the alternator itself while it's firing, like at least a foot away, you're going to be absolutely fine. So, but most things are, they do just fine with those normal stuff. I did want to talk a little bit about mental health, that it was brought up too. So kids and teens with ICDs and reports have reported a lower overall psychosocial and physical quality of life compared to healthy children who have taken the same survey. The medical severity of those kids with ICDs, or if they use the ICDs, having appropriate or inappropriate shocks, did not tend to impact their scores. And so kiddos are affected by having a condition that requires an ICD, and they look at themselves as being less healthy, and they are more vulnerable to psychosocial issues and having restricted behaviors or being nervous about certain activities and things like that. But what I will say is actually the kids indicated that they were doing better than their parents thought they were. So we gave the same scores to the parents, and the parents thought that they were more sick than the kids actually thought they were. And so that's one thing that you have to look at as well. I think ICDs are a good thing, a good tool that we use when we absolutely have to. And so the way I frame it for my kiddos is that I hope it's a helper device and not something that is thought of as a burden. My hope is when I implant it is that I give kids freedom to live their life in a more free and anxious-free way. And I do ask them to take responsibility to care for that device so that nothing bad happens to it. But I try to frame it that way. And I think that that's a better way. We always try to work to avoid ICDs when possible. And so when they're necessary, I think that framing it a little more positively is how I've worked. In addition, I want to say that I'm here to help, or we're here to help. The SADS Foundation has a wonderful website full of informationals about these. They have groups of individuals farther along this path, if you haven't had an ICD, that can talk about real life experience. And then the PACES Society, or Pediatric and Congenital Electrophysiology Society, pacesep.org, also has a good website, and they're partner organizations. SADS and PACES are not competitors, they're friends. And all of the members are coexisting there, and also has a good network of individuals and also places to read about certain things. So with that being said, I'll pause and stop sharing, and I'd be happy to answer any questions. Let's see how I can do with this.
Thank you, Dr. Howard. We do have a couple questions, and then we have one person that would like to ask verbally. So from Motion, what coil do you use for epicardial ICD? Are you muted, Dr. Howard? Unmute yourself.
Oops.
There you go.
All right, there we go. Sorry. I said what I said was really good before. I'm going to say it again.
Please repeat.
So it's the coil that we use is the Boston Scientific subcutaneous coil. It actually functions almost exactly like a transvenous or traditional lead coil, but doesn't have a screw on it. And it's a little bit bigger. The size of the coil is a little bit larger, so it's able to take a little bit more of a shock. And we place it just next to the sternum, below the subcutaneous tissue, but outside the chest wall. So I hope that answers the coil. Oh, and it was looked like what coil to use for an epicardial ICD. The epicardial ICD coil is the same as the transvenous coil. So, you know, in Medtronic, it's a slim line, and Abbott has their own coil. So it's the exact same coil that's used. It's just placed behind the heart for a better vector. Good question. What else?
Okay, Darren asks, I have a transvenous ICD lead that has been cut and capped, and it was placed 22 years ago, and removal risk was very high. His question is there research into the ability of S-ICDs to provide bradycardia ATP pacing or some sort of leadless pacing cardioversion ICDs?
Darren, I like you so much. We're getting into the weeds here on this. So this is a great question. I probably should have gone a little harder at you guys. So the answer is yes. So the Boston Scientific current version that's released does not have anti-tachycardia pacing. ATP is anti-tachycardia pacing. It can do post-shock pacing, and it's programmed to do it about 3.5 seconds. So if you get shocked, it waits 3.5 seconds. And then if it doesn't hear a heartbeat, it starts pacing, but it paces the whole of the heart because it's a pretty big device. Companies are now racing to get in the game because Boston Scientific has been the only provider of an FDA-approved S-ICD system. So Medtronic just released their own. Their coil is placed a little bit differently. It goes actually under the sternum inside the chest wall. The reason I didn't talk about it is because we haven't used it in children or young people yet, but it does have anti-tachycardia pacing ability. I have not seen the clinical trial result yet to know how well that did, but it does have ATP as a part of it with the Medtronic subcutaneous device. Then the next thing coming from Boston Scientific is to actually pair a leadless pacemaker with a subcutaneous ICD. And so they Bluetooth to each other. And so you insert a leadless pacemaker into the ventricle, and that provides ATP. And in case of ATP failure, then the subcutaneous device leads to a shock. And that is rapidly going to be on the market soon. The trials are going on. I would expect that in the next year or two. There's already, the people in trials are already doing that. And the Medtronic device, I think, may be coming available, maybe available now through it, but I don't have any experience with it. So yes, that there are solutions coming to that for individuals like Darren who might have difficulties because of previous ICD management thing. I want to meet you, Darren. I like your questions.
Okay, thank you, Dr. Howard. Okay, Victoria has a question she wants to ask verbally. So Victoria, you can go ahead and unmute yourself and ask your question.
Okay, sorry, I was trying to figure out how to unmute. So my question is, I guess I don't know really how to ask this question. So I had an S-ICD. And I got shocked 12 times inappropriately, and I was wide awake for all the shocks. And I guess I had them remove it. Like, it was a patient decision to have them remove it because I had such bad PTSD from the shocks. And I still have, like, if I hear like loud popping or something, it still causes me to have like really bad PTSD episodes because I was awake. So I guess my question is like, what would you suggest as to like, what are my other options? Because I guess my electro doctor, all he's suggesting is you just need to get another ICD. You have no other option and everything. And it's just like very hard for me mentally because of having PTSD so badly from the shocks.
Yeah, Victoria, I hear you. I'm sorry about that. You know, devices are not perfect. And despite us trying very, very hard, there are inappropriate therapies that come into play, and sometimes they happen back to back like that. And so your PTSD is unfortunately well earned on that. Now, you have to make your own decision, and I won't make you overshare, but your condition or the type of condition that you have in order that requires an ICD, or at least the conversation, is very important about talking about your options about avoiding a device in the future. I will say that occasionally subcutaneous ICDs have vectors that can't sense as well. They're less nimble than transvenous ICDs. And so there's not head-to-head comparisons, but we do think that S-ICDs may have, may be less nimble as far as their programming, and it may have a slight increased inappropriate shock rate, although that's hard to prove in our population compared to transvenous. But it doesn't mean that any ICD can inappropriately shock you. And like I said, it's not zero. It's probably 9 or 10% of individuals if you have enough exposure time. If it's going to change your mental health in a way that you can't function, then you have to make that decision for yourself. But there may be options that are available for you. And really what I say is, somebody that does this a lot and works with a lot of people, I don't think second opinions are a bad thing. Your doctor's trying to take care of you and make sure that you're safe. And but they, if you're wanting to figure out if this is the only option moving forward, and if you have to feel settled about that, then it may be an opportunity to talk with another person as well about that.
Thank you so much.
Yeah, absolutely.
Thank you, Victoria and Dr. Howard. And we have another question from Amy. Many doctors do not mention that incision pain from ICD surgery can be a side effect from the surgery. She's had her ICD for many years now and still experiences incision pain. What do you do for patients with this pain?
Yeah, thank you for sharing. I didn't put that in, Amy, because it's a rare complication, but you're right to say it is. So incisional pain is something that we do see less than 1%. It's less than 0.5%, but it's 0.1 to 0.2% of adults after ICD implantation that come in. So there are a couple of different things that you can do. If it gets so bad, then you can do pocket relocations, or you can either from transvenous to subcutaneous ICD, or you can try to relocate the pocket to an axillary pocket or under your armpit and see if you get better luck from the second incision, but you still kind of run that risk over again. There is not good, you obviously can't do injections around that site, and we avoid lidoderm patches and things like that over that area. But if it gets so bad, then I've not had to do this myself, to be honest with you, but I've heard about individuals moving the pocket to another location. But that's a big thing you got to be thoughtful about. But thank you for bringing that up, because I needed to put that into correct so everybody understood that as well.
All right, thank you. Ryan asks, his alert sound was disabled from an MRI. How do I know if it's temporarily disrupted?
Well, they should, after an MRI, and you put the ICD into something called SureScan mode. If it's Medtronic, that's a proprietary statement, but Abbott and Boston have the same kind of deal. So MRI compatibility mode. After that, they take it out, and you should have your alarms reset to be normal after that. And so the way that you can check it is you could probably send in a wireless transmission using your transmitter and make sure that your alarms are set normally. And if not, you can get downloaded by your pacemaker team and make sure that they just reenact those kind of alarms, if I'm getting this question right.
Sounds good. All right, so Jen asks, why don't the ICDs alert emergency contacts when they shock or sense an abnormal rhythm? How can we work to making this possible?
Well, I think that's a great idea. And so, with the availability of now Bluetooth communication with your cell phone, and looking at Apple, when they sent something on Apple, like a car accident, they call contacts and things like that, I don't think that's a bad idea. If you will partner with me, I think we could go sell that to Medtronic for a bunch of money. How about that? Would that be okay? We could say it's our idea instead of yours. But I do think that that's a smart thing. There may be some firewall issues surrounding that as far as how it communicates with certain devices that would be our issue. But I think that's a really good idea.
All right. I think that concludes the chat questions that we have so far. So I really appreciate you figuring out your PowerPoint there and the firewall there at Texas Children. So thanks for spending your Saturday with us and addressing some of these questions.
Absolutely. All right. Well, it was a pleasure to be here. Thank you guys so much for having me.
Thank you, Dr. Howard. Okay. Next, as I mentioned earlier, our gene therapy talk by Dr. Mario Delmar will be a recorded message. He was unable to be with us today, but he recorded it earlier this week. He is the Martison Endowed Chair and Professor of Cardiology at NYU Langone. And so we will be sharing his recording about gene therapy. And I'll put in the chat, because he did say that we could share his email, which is mario.delmar@nyulangone.org. So we'll put that in the chat for you. Meanwhile, Aaron, I'll let you share the recording.
All right, so let me start by thanking the SADS organization for inviting me to present today. I am sorry I cannot do it during the live session, but I am really very happy that that I was invited to do it on a recording. My presentation today will focus on gene therapy for a particular condition that has been the topic of investigation in my laboratory for the last 20 years or so, and that is arrhythmogenic right ventricular cardiomyopathy, which I will abbreviate as ARVC. What I will do today is to describe the disease and the function of a particular gene that is called plakophilin-2 that plays a major role in that disease. I will then describe a mouse model that we generated some years ago and continue to use for the study of the consequences of the deficiency of plakophilin-2 in the heart, and how this model has served us to test therapies. I will talk a little bit about medical therapy, and then I will focus on gene therapy. I will finish then by describing our studies on gene therapy for ARVC, and then the reasons for cautious optimism. And I highlight the word cautious because there are some caveats that I think deserve careful attention. So this is an image of the heart afflicted with ARVC. This is an MRI of the heart. This is the left ventricular chamber. This is the free wall of the left ventricle. So this heart is showing an MRI section along the long axis of the heart. So this is the septum. And this would be the ventricular chamber, the right ventricular chamber. And you can see that instead of a muscle texture, it has actually been substituted by this loose tissue that, if you look under the microscope, shows this anatomy. Instead of being all muscle, which would be red in this image, there is a lot of this whitish tissue that is fat, adipose tissue. And these blue stains that are actually collagen, it is fibrous tissue. When you look into the left ventricle, most of it is muscle mass, although you already see some infiltrates of collagen and fat. Very importantly, in the early stages of the disease, because the left ventricle is still okay, this is a very dangerous condition because patients do not know that they have the disease, and yet at this stage, the disease is highly arrhythmogenic, and it can be the cause of sudden cardiac arrest or life-threatening ventricular arrhythmias. ARVC has been linked in those cases in which a gene is identified to mutations in proteins of the desmosome. The desmosome is a structure that holds cells together, one cell to the other. Best example of desmosome is the skin. If I pinch my skin and I lift it, the cells do not rip away from each other because they have desmosomes that hold them together. Imagine it as Velcro between cells. Inside, the cells are connected to a very flexible fiber called, in the case of the heart, desmin, in the case of the skin, keratin. So not only do the cells not rip off from each other when I pull my skin, they actually stretch because desmin stretches. And then when I release, they go back to the original position because the desmin allows it to come back. Now, about an estimated 50 to 70% of cases of familial ARVC where a gene is identified, the mutation is in the gene coding for this protein, plakophilin-2. And ventricular arrhythmias are the first manifestation in disease in about 50% of the cases. So we have been very interested in investigating what are the mechanisms that lead to this very arrhythmogenic condition where mutations occur in a protein that is rather structural. I will not go in detail through that, but will describe the model that we have used to study this. Some years ago, we generated a mouse model of plakophilin-2 deficiency. These are mice that are born with a natural plakophilin-2. We do not disrupt their plakophilin-2 during development. When they are about 3 or 4 months of age, by a technique that I will not detail, but it is basically a technique that allows us to knock out a gene in a particular type of cell at a particular time point in the life of the animal, we inject them with tamoxifen. That is going to knock out plakophilin-2 only in the cardiac myocytes, in the cardiac muscle cells. We do this when the mice are about 3 or 4 months of age. That is, they are young adults at this stage. And we do it both in male and female mice, and we have not found a difference between the two. Now that we have knocked out plakophilin-2 only in the cardiac cells and already in a young adult animal, we have a sequence of events where we are going to monitor these mice for heart function and for survival. And we're going to use then echocardiograms, we are going to use electrocardiograms, and we are going to evaluate fibrosis post-euthanasia. And I am not going to talk about the fibrosis other than in the conclusions. So what happens with these mice? Remember, day 0 is going to be the day that we injected them with tamoxifen, the day that we begin the knockout of plakophilin-2. So 14 days after we knock out plakophilin-2, this is easy, nothing happens. This is a section of the heart, free wall of the right ventricle, free wall of the left ventricle, all muscle. In the panel on the right, what I've done is to exaggerate the contrast on the blue, on the collagen, on the fibrosis. And at 14 days, you can see that there is no fibrosis. This heart is as good as a control. But 1 week later, then what you observe is that there is quite a bit of fibrosis, quite a bit of blue on the free wall of the right ventricle, extending all the way to the tip where there is some form of an aneurysm. Yet the left ventricular wall is maintained pretty much intact. So this is the cardiomyopathy of right ventricular predominance that results from the loss of the plakophilin-2 gene, which is the main cause of ARVC in humans with a genetically identifiable ARVC. So this is what happens by echocardiogram. Again, time 0 is the day that we inject them. They are young adults at this time, and now we're following in time and days post-injection. 14 days post-injection, I showed you the picture. There is a slight dilation of the right ventricle, but that is all really that we see. It's very minor. But then the right ventricle continues to dilate with time, progressively bigger and bigger. And the last time point that we recorded was 42 days, and I will show you why. If we look at the function of the left ventricle as a pump, indeed, we start to lose function in the left ventricle at about day 21, But then it decays even further and further and further. And again, by day 42, the ejection fraction, the ability of the heart to pump, has decreased to about 20%, when in the initial condition is somewhere between 50 and 60%. And this is what happens in terms of the survival of these mice. I showed you the function at day 28, the heart at day 21, pathway day 28 or 30, all of the mice are alive, but then around day 32, we start to see lethality. We start to lose more and more mice. There is less and less survival. And by day 50, we have 100% lethality. The mice die in end-stage heart failure. The controls in the black line, of course, continue to live, and they would live much longer, but we interrupt at the time of 100% lethality. Are they arrhythmogenic? The answer is yes. If we try to induce arrhythmias by injecting them with this drug isoproterenol, which is a mimicry of a catecholaminergic, of a stress by adrenaline, they start to develop arrhythmias, some of them very severe, in some cases leading to ventricular fibrillation and death. Not all of them, though. Most of them do have some arrhythmias during this period of injecting them to stimulate their adrenergic response, but in some cases only they develop more severe arrhythmias. Now, when you have a mouse model of disease, you have a great tool, a tool that allows you to test for the effects of drugs. And for defining a drug, we abide by a very clear definition of a drug that was provided by Otto Loew. Otto Loew was a very famous pharmacologist who actually discovered one of the major neurotransmitters in the body, acetylcholine. He won the Nobel Prize for that discovery. He moved from Austria because of the war to NYU, finished his career here. And he was asked, what is a drug? And he thought for a moment, and he thought, well, a drug is a substance that when injected into an animal produces a paper. And we had considered what would be the right drug to test when we were generated our first papers. And we knew at this point that ventricular arrhythmias in these mice result from a mechanism called triggered activity, which is that there is an imbalance of the control of calcium inside the cell. And when the calcium is such an important element in a heart cell, if there is too little of it, bad things happen. If there is too much of it, bad things happen. The cell has all sorts of mechanisms to maintain calcium in a very, very tight balance. And when the calcium is too much, that can lead to very severe arrhythmias. We found that indeed there is such an imbalance of calcium release in these cells. Using this model, then we decided to try a drug called flecainide, because this drug can prevent arrhythmias in a twin condition called CPVT. We did try flecainide, and we found that flecainide abolishes the ventricular arrhythmias in plakophilin-2 deficient mice. I give this as an example of why these mouse models can serve as preclinical tools to advance to the clinic, because with these experiments and with other anecdotal evidence in patients, Wojciech Zareba and Hugh Calkins led an effort of a pilot randomized trial with flecainide in ARVC patients. This trial ran for a couple of years, and actually Dr. Zareba at the last FHRS meeting presented the results of the late-breaking clinical trial. And the results were, just with his permission, showing one slide that shows that the number of ventricular premature beats in a day, both calculated by the mean or by the median, significantly decreased when the patients were receiving flecainide, as well as the number of ventricular tachycardias per day. So this has given us a little bit of a boost of confidence that this mouse model can serve as a preclinical tool to identify future therapies. Now, what I have shown you with the flecainide is that we can repurpose known drugs. Flecainide is a drug that has been approved for many years. It also should allow us to develop new chemical agents. In the treatment of diseases, it's possible to develop new chemical agents with a therapeutic effect. In the last several years, though, there has been quite a bit of excitement about the idea that one can deliver not a drug, but a gene to the cells that need them. And this is what is called gene therapy. For gene therapy to be successful, you need basically three things. You need a deliverable. That is, what are you going to deliver to the cells? In our case, a healthy or a reparative gene. You need a vehicle. And the vehicle is going to be an adeno-associated viral particle. This is not a virus. This is not going to cause an infection. The virus is not going to be able to enter the cell and replicate. It is only a part of the virus that can identify the right cell and deliver the DNA, but the virus will not continue to grow. It's only a piece of it, an adeno-associated viral particle. You also need an address. You need the address of something that will tell us that we can target the cardiac cells only, because we don't want to deliver this gene everywhere in the body. We want it to be delivered as specifically as possible to the cardiac cells. This is kind of what UPS does. They have to find a deliverable that you ordered, a vehicle, and they need your address. The thing is, the heart is a good target for gene therapy because there is no cell division. When the gene enters the cardiac cell, it stays there. In cells that divide, like cells from the lung, cells from the liver, cells from the intestine, pretty much for most cells of the body, they have the ability to replicate, to make new cells. One of the complexities of heart disease is that we cannot regenerate the heart muscle. And so the heart muscle stays put. And if you lose some, that's loss. But in the case of gene therapy, at least we get one advantage, and that is when we get the virus in, it stays in. It doesn't go anywhere. And so it keeps making the gene that is missing. And that gene is going to code for a protein that is going to live the natural cycle of the protein, hence replacing the gene that is missing in that body. There are variations of gene therapy. One is gene replacement. That is, the defective gene does not code for a protein. So you introduce a gene, now the protein is coded and is provided. Gene supplementation, where there is a native gene, but is coding for a defective protein. So with a new gene, you seek to substitute it or to overwhelm the defective gene. Very exciting new developments in gene repression replacement, which is to try to silence the gene that is mutated that can be causing negative effects, and at the same time express the gene in its healthy form, so that you repress and then you express. There is a different way of doing gene therapy, that is to code for a therapeutic molecule. So it's not replacement of a gene, is that you introduce into the cells a gene that will code for a medicine, so to speak. I am going to be talking about gene replacement. It is very important for me to make clear that the next slides were obtained in collaboration with a company by the name of Rocket Pharma. These are the scientists at Rocket Pharma. This was sponsored by a research agreement between Rocket Pharma and the NYU Grossman School of Medicine. So all financial exchanges were made between the organizations. To us at NYU, there is no past, present, or future royalty obligations at all. This was made completely under total academic independence. So what we did is that we took an adeno-associated virus and we injected it by a single tail vein injection. So a single injection in the tail vein of the mouse, either the formulation buffer or this particular type of AAV. And I will hopefully mention why that is important. Now, without going into too much detail, when you take a normal heart section and you look for where plakophilin 2 is, you see these red lines abundantly in between heart cells. That is where plakophilin 2 is. That's where the desmosomes live, at the end, at the point of contact between cells, in these big red lines. In the knockout mouse, in the one where we have eliminated plakophilin 2, you do not see those red lines. But in hearts where we reintroduced the gene by means of the AAV, we again see those red lines. So the gene codes for a protein that is able to find its way back to the right position. Importantly, we do not get 100% infection. You see, there are areas where we do not see the signal of the plakophilin 2. Yet, with about 50–60% coverage, that is what we get effective results. This is perhaps the most important slide. In this case, we injected the AAV either 7 days from the beginning of the loss of plakophilin 2, or even 14 days after the beginning. And remember, 14 days was a critical day, is the day at which we saw the very first earliest manifestation of disease by this dilation of the right ventricle. And in those mice that we injected just with a buffer, not with the AAV, we see the mortality that we described before. But in the ones that we injected with the AAV, either at 7 days or at 14 days, these mice continued to live, and they survived up until day 150, when we terminated the experiment so that we could study those hearts. So we went from 100% lethality to 100% survival when the AAVs were injected either 7 or 14 days after we knocked out plakophilin 2. Remember that the RV, the right ventricle, gets dilated when we do not have plakophilin 2. And this is how the area of the right ventricle increases 28 days after tamoxifen injection. When we injected the AAV 7 days after tamoxifen, we were able to completely blunt that dilation of the right ventricle. And even the mice that we injected 14 days after tamoxifen, that is, when the earliest manifestation of disease appeared, we were able to blunt the dilation of the right ventricle, even when we recorded it 5 months after tamoxifen. So when the mice are 8 or 9 months of age. When we looked at the left ventricular function, at the ability of the heart to pump blood from the left ventricle, remember, in the knockout, there is a drop of ejection fraction. There is a loss of function. This loss of function is quite mitigated when 7 days or 14 days after the loss of plakophilin, we injected the AAV. You can see that that effect persisted up to 5 months after we injected the animals. So we do not recover heart, but we stop the loss of function because we stop the loss of the structure of the heart. Is this an antiarrhythmic effect? The answer is yes. The animals injected just with buffer have a lot of arrhythmias, but the ones in which we replace the gene have much less arrhythmias, less than 100 PVCs, which is sort of a margin that we artificially at least established. So I have presented data showing that AAV RH74 mediated PKP2 delivery arrested the progression of the right and left ventricular cardiomyopathy, reduced arrhythmia incidence. I did not show you the data for reasons of time, but it arrested the progression of the fibrosis, and it drastically improved survival from 100% mortality to 100% survival when we delivered the gene. In May of 2023, the FDA endorsed a request by Rocket Pharma for an IND, in other words, a permission to move on to clinical setting. And thus that has enabled the clinical trials, and Rocket Pharma has a phase 1 activity ongoing. Now I want to finish with these lines. All models are wrong. Some are useful, and this statement by a famous statistician, George Vaux, remains not only true, but it remains perhaps a mantra that we have to keep in mind. Of course, our model is wrong. It's a mouse. Not only is a mouse, it's a mouse that has only lost plakophilin-2 in the heart, and it has lost complete plakophilin-2. It's not expressing a mutation. Anyway, there are a number of reasons why our model of ARVC is wrong. The point is that it can also be useful not to recapitulate all of the features of ARVC, but to study the cardiac phenotype, the cardiac manifestations that depend of a gene that when it's mutated causes ARVC. And then we can use that knowledge to generate preclinical data that can guide alternatives to therapy. In this regard, it is also important to mention that there is reason, in my opinion, there is reason for optimism, but there is very good reasons for being cautious about it, because there are a number of steps that need to be taken in the clinical process before a patient is subjected to gene therapy. The importance of the ARV-RH74 has been that it comes from a rhesus monkey, so we humans may not have as much antibodies against it as if we use AAV9, that is the most commonly used AAV, and for which many of us may already have serology positive, and therefore it wouldn't be practical. But we have a lot to learn, and again, this is just an opportunity to get initiated in a path that hopefully, with time, will lead us to the implementation of gene therapy for patients in need. And with that, I just want to thank you again, the SADS Foundation. Thank you very much for listening. And again, my apologies for not being there in real time. Thank you.